So some of the challenges that we see in HPC fault tolerance, obviously compute nodes still are going to be able to fail. Right? You still have probably one of the bigger failure points within the compute nodes is going to be the memory. Right? You can still have a CPU failure, you can have a bridge failure, you can have multiple points within your compute nodes that can continue to fail. Checkpointing, right, is a very big issue, right, for a lot of these larger systems. It's very easy to be able to do, it's relatively easy to be able to do a checkpoint, right? And you're just going to dump the state of your compute node. But the problem continues to be that, you know, even if you're building that into the application, which isn't a trivial task, or if you're running an application that is going to be able to do checkpointing, the problem is that now you have to take that checkpoint data and you have to put it somewhere. Right? So now you have to push it out to storage. And the amount of time that it takes to push it out to storage, particularly as these nodes continue to grow, and you get nodes with 32 or 64 gig of RAM, the checkpoint image gets extremely large, right? So the amount of time that it takes to run a checkpoint becomes prohibitive. And then finally, the fabric reconfiguration versus true adaptive routing. So that's one of the problems that needs to be, we see it being really needs to be fixed. So in a lot of the InfiniBand fabrics today, you can do reconfiguration of the network, right? But that's going to take down the job, right? It's going to potentially interrupt things that are going on within the fabric, right? Because you're going to re-provision the system and rebalance and reallocate routes, right? Within the routing tables within the switch chips. And you really need to be able to almost instantaneously route around the problem, right? So that jobs don't fail, so that jobs can continue to run and find a different path. Even if it's going to create some level of congestion, at least the job will be able to finish or get to its next checkpoint. So that's the main portion of the presentation.
Yeah, I was just curious as to what you see in terms of mean time between failures and how does that work when you scale up. Do you have any data on that? Because that's kind of like if you talk about checkpointing intervals, that's kind of, I think, a significant thing to consider.
Yeah, we have a lot of MTBF data, not only of nodes, but also of InfiniBand switches and cables and all of the parts and pieces. So you can really calculate out what the MTBF of a full cluster would be, you know, the uptime of a cluster. And obviously, as it continues to grow, that number gets smaller and smaller. But we definitely have data that we can share.
I've noticed that a fair number of the failures we see are things where, you know, the batch system thinks the job is still running, no error has actually been triggered, but some portion of the parallel job has gone catatonic and it's not detected. Do you think that in the future you'll be able to detect a higher percentage of that sort of error? Because right now, I think if it scaled up too much further, those would be happening all the time.
I think you've hit on one of the key challenges of providing fault tolerance in these big systems, and that's the software. And so much of the software seems to have been designed kind of from the bottom up without fault tolerance in mind, and often the approach is to come back in and try and patch the software or implement things on top of it to try and handle that. I mean, even if you get down to a simple level of, you know, you're trying to add fault tolerance to your system and you're going to add 2 Ethernet networks to it. Well, you sit down and you plug in 2 Ethernet networks and you start doing and you pull one out and, well, wait a minute, I thought I had fault tolerance. Well, it doesn't really handle that. You have to go install new drivers, new software, because the drivers weren't written with that in mind. They're kind of, everything's written with the simplest case. So, I think that's one area that we really have to do a lot more work on. One of the approaches that we're taking is you look at some of the challenges with the HPC software stack. There's so many protocols there for dealing with doing disk I/O or network I/O, and so you end up, even if you provide fault tolerance at one level, it doesn't take care of the fault tolerance at other levels. And that's where we were thinking that OS support or doing things, shortening that stack, getting it down to, let's provide fault tolerance more at the system level from the ground up. Now even those things aren't necessarily going to fix a batch system problem. I know there have been work for batch systems. We're just trying to configure the batch system so that it can detect black holes, where you've got one node that's just eating jobs, and so you have to kind of put in a monitor for that. And in general, if you can configure the system to kind of monitor itself, that will often help with those particular cases. But we just have to look at it from the bottom up and say, what are the features that we can put in at the lowest level to take care of this fault tolerance, so that we don't have to re-implement fault tolerance at every single level of the system. MPI is kind of a convenient place to handle it from a pretty high level, because that catches, for parallel jobs, that catches quite a bit of the issues. But that only provides network fault tolerance. That doesn't provide, if your compute node fails because the BIOS was different on this version than the other computer versions. So right now there's just a lot of different areas that we have to attack from, but we want to move toward attacking it at a system level.
One other aspect of that, actually, one of the pieces that people tend to do is they tend to put a monitor out there. But whenever you start scaling up to large numbers of nodes, a lot of the current system designs start throwing out those monitors because it increases jitter in the OS. And so you actually end up having the very people that want and need the reliability throwing out pieces of the system that were designed to improve the reliability. And so that's going to be one of the big issues as systems grow up toward the exaflop level, is how do you solve that problem where you need a monitor, but it can't increase the OS jitter.
I just got a quick question about cost analysis. Have you done trade-off studies on implementing this type of fault tolerance instead of just buying more disk, for example? We had a project where they lost disk, and it was cheaper than actually 10 gig infrastructure. So I was just curious if you had any justifications that we can use for future projects.
I don't think we've really done a true cost analysis. I mean, we Appro anyway, we offer multiple levels, right? So when we talked about the fault tolerance capabilities, we offer single and dual management nodes, single and dual sub-management nodes, single and dual Ethernet, single and dual InfiniBand. So we've got all of those, and when we work with our customers, we try to offer them all of the different ones, and then it's really up to the customer to understand where their pain point is for the dollar. Right? It's kind of like when you look at storage is a great example, because you're trying to balance throughput versus reliability, right? Do I go with a RAID 1, or do I need a 5, or even higher, do I need a 6, right? So you start making those trade-offs, and it's up to us to help give you those options and help you understand what the impact is if you don't take it, and and then it's up to the customer to make a decision, you know, well, I do a lot of checkpointing, so I don't need that level of fault tolerance, or I have jobs that are critical and they run for long periods of time, and if one dies, you know, I'm dead, right? So it's a fine trade-off, and it's not just about dollars and cents, so it's too hard to put a number on it.
Point. So always the dual system costs double of the cost, right? But what I'm thinking is that not just doubling the system. For example, let's think about the difference between the RAID 1 system and the RAID 5 system. So RAID 5 system is much better for the cost effectiveness because the RAID 1 system always just one additional disk is only the copy, but the RAID 5 system is distributing of the error failures and recovery of the values. So one idea is that making the computation node much wider or much fat configuration with multiple sockets. So we have a much higher performance on the node. So of course, then we need a much higher bandwidth on the node. So it means that not just a double or a quad layer, for example. And if only one layer fails on the quad layer, we lose only 25%. So we can survive with 75%. So I think it is some better way to make the node shrinking into the small performance and the small number of the rails, or make the large number of sockets and to make large number of rails to recover the failure and to make the good balance of the cost.
So yeah, we have some questions that we prepared a bit to try to talk about other questions or other items. And if you want to say something, if you want to give your opinion, more than welcome. I brought a couple of T-shirts for people who's going to ask questions, so I think I already free. Just to encourage you, that's what the T-shirt says. I think it's nice. And that's so I have a couple of T-shirts here. The first question that we want to raise, and anyone from the panel can take it. We all know that there is a need for fault-tolerant supercomputers, right? We talked about it here. But to reduce complexity and cost, there are key components in the architecture that is a must-have for a fault-tolerant machine. So in your opinion, what is the main component, hardware and software, that addresses the main pain points for a fault-tolerant supercomputer?
I think this is very close to the question that he kind of already asked, right? So it really comes down to how much fault tolerance can fit within a budget. And there's some that are very easy and give a lot of return for investment, right? So fault-tolerant power supplies, for instance. Relatively low investment, but good bang for the buck because of the failure rate of power supplies. Redundant management nodes, right? Very good bang for the buck because if you lose that one node, you lose the entire cluster. So you can almost put a weight to all of the different parts and pieces that we've talked about and be able to kind of determine as you work your way down through the budget exactly, you know, how much can I afford out of all of the possibilities.